Throughout the universe, there are more than 2 trillion galaxies, each one holding hundreds of billions of stars. And around those stars, there are worlds beyond counting, billions upon billions of planets, each circling its own sun, each carrying a history of birth and change. Most of these worlds follow the rules we expect: rocky, Earth-sized spheres, or gas giants like Jupiter. But scattered among them are the outliers, the ones that bend or break those rules completely. Some are too large, some cling too close to their stars, and some are so light they should not even hold together. By the standards of our current science, they have no right to exist, and yet they do. The signals are strong, the data precise, and the truth they carry is unavoidable. Welcome to the Drowsy Astronaut. Tonight we journey through these impossible worlds, exoplanets that force us to question what planets are and how they can survive. While you relax or even fall asleep, your subconscious will wander among planets that should not exist, worlds our science still struggles to explain. So, let us begin. Our first stop is WASP-12b, a swollen giant circling its host star in just over a single Earth day. It resides in the constellation Auriga, about 1,400 light-years from Earth, so far that the light we see began its journey in the medieval age of our own history. The star it orbits is a yellow dwarf, close to our Sun in mass, but slightly hotter and more energetic. The orbit is tight, less than 1/20th the distance between Earth and the Sun, close enough that gravity stretches the planet and starlight strips away its air. Astronomers classify WASP-12b as an inflated hot Jupiter, a planet with roughly the mass of Jupiter but swollen to nearly twice its size. Its measured density is only 0.3 grams per cubic centimeter, lighter than water, lighter even than the wood of a tree, making it one of the least dense giant planets ever recorded. The planet was first discovered in 2008 by the Wide-Angle Search for Planets survey, when astronomers noticed its star dimming at regular intervals, the unmistakable sign of a planet passing in front. That dimming revealed its radius, while careful measurements of the star's slight wobble revealed its mass. And together they painted the picture of a giant world puffed up far beyond what standard theory could explain. The heat from its star is the obvious culprit. At over 2,500 Kelvin, the day side is hot enough to vaporize metals, a temperature where even titanium oxide and iron may rise into the air. The planet is locked into synchronous rotation, the same hemisphere always facing its star, an eternal day and an eternal night. Infrared data reveal a hot spot shifted eastward from the substellar point, a clear sign that winds roar across the atmosphere at thousands of kilometers per hour. These winds are not gentle breezes, but supersonic streams. They carry heat into the dark hemisphere, where no sunlight reaches, raising temperatures there to levels that would melt rock on Earth. The circulation shifts the brightest spot away from the center, proving that the inflated atmosphere is not static but moving. It is a climate unlike any imagined before transits revealed these maps, a system driven by constant starlight and constant loss. The atmosphere itself does not stay bound. Ultraviolet spectra show a faint tail of gas streaming behind the planet, just like a comet's plume. Each second, millions of tons of hydrogen are lost, carried outward by the heat and radiation of the star. The loss is not metaphor, but measured fact. Transit depths deepen in ultraviolet light, showing the escaping envelope around the planet. If you could somehow stand within its atmosphere, the view would be overwhelming. The host star would fill half the sky, a blinding disk so vast that no horizon could escape its glare. The air itself would not be clear, but glowing, heated until it shimmers orange and red, with currents racing faster than sound. Around you, the horizon would blur, stretched into haze by tides, and above, faint trails of hydrogen would drift outward into space like the ghost of a comet's tail. There would be no silence, no stillness, only a furnace world unraveling beneath a star too close to resist. The Roche limit is the invisible boundary where tidal forces can tear a planet apart. WASP-12b orbits uncomfortably close to this line, its body stretched into an oval, its orbit already showing measurable decay. Astronomers watch as the transits arrive slightly early each year, evidence that tides are steadily draining energy from the orbit. Within only a few million years, the planet may plunge into its star, its swollen body consumed completely. The chemistry makes the story stranger still. Spectroscopy reveals carbon compounds dominating the atmosphere, methane and carbon monoxide outweighing water vapor by wide margins. This makes WASP-12b a carbon-rich giant, unlike Jupiter, where oxygen and water vapor shape the chemistry. Models even suggest that deep inside it could rain graphite or diamond, exotic storms hidden beneath the blistering haze. If a person could somehow stand in such a storm, survival would be impossible. Graphite flakes, sharp as sandblasting grit, would scour exposed skin driven sideways by supersonic winds. Diamond shards, small but impossibly hard, would strike like needles, embedding into anything they touched before sinking away into deeper layers. Add to this the searing heat, hot enough to vaporize stone, and within seconds flesh would char, lungs would fill with toxic gases, and the body itself would be torn apart by pressure and wind. On WASP-12b, rain is not cleansing, it is fatal. Such chemistry implies a disk unusually rich in carbon-bearing ices, a birthplace very different from the pantry of our own solar system. The inflated radius remains another puzzle. Gas giants should cool and contract with age, yet this planet remains oversized long after formation. One explanation is ohmic heating, where charged winds moving across magnetic fields drive electric currents into the deep interior. Another is tidal heating, energy released as the planet flexes under the stress of its decaying orbit. A third involves atmospheric opacity, with molecules in the upper layers trapping heat and slowing its escape. The most likely answer is that all three processes combine, conspiring together to keep the world swollen. Think of a balloon held too near a fire. It swells as the air inside grows hot. The skin thins, faint streams escape, the shape trembling at its limits. WASP-12b is that balloon on a planetary scale, its atmosphere stretched outward until the edges blur into space. Radiation strips molecules one by one, leaving behind a faint halo of hydrogen around the planet. The Hubble Space Telescope confirmed this extended cloud, a direct observation of atmospheric escape in action. The planet's current location is best explained by migration. No giant can form so close to a star. The heat of that region prevents the condensation of gas and ice. WASP-12b must have been born much farther out, beyond the frost line, where ices could solidify and cores could grow. Over time it drifted inward, carried by currents in the protoplanetary disk or pushed by gravitational encounters with other planets. Its present orbit is an accident of history, not its birthplace, but the position that sealed its fate. Picture a train line cutting through a crowded city. Passengers board on the outskirts, yet the flow inevitably carries them inward toward the center. Planets follow the same invisible motion, drawn along the currents of gas and gravity, bound to paths they cannot resist. WASP-12b is one such traveller, once cold and distant, now hot, fragile and trapped near its star. The weather on this world is extreme beyond comparison. Phase curves reveal a blazing day side near 3000 Kelvin, hot enough to vaporize stone into gas. The night side is cooler yet still a furnace, glowing above 1000 Kelvin, heated by winds instead of starlight. Supersonic winds shift the hottest region by dozens of degrees, proof of atmospheric circulation that never ceases. The chemical balance adds another subtle clue. Its high carbon to oxygen ratio signals a birthplace unlike our solar system. Jupiter is oxygen-rich and thick with water vapor, but WASP-12b leans heavily toward carbon. It must have formed in a disk where carbon compounds dominated, creating chemistry that feels alien to us. Tides shape the orbit with relentless force. The star's gravity keeps the rotation locked, one side burning in endless day, the other forever in night. The planet's figure is distorted, stretched from a sphere into an elongated oval. Each year the orbit shrinks slightly, angular momentum bleeding away under tidal drag. Within a few million years, it will finally fall into its star, ending in fire. The contrast with Jupiter shows the scale of the anomaly. Jupiter's radius is about 11 Earths, but WASP-12b swells to nearly 18. Jupiter's mass is 3 times higher, yet its density is far greater. WASP-12b is lighter than water, barely denser than wood, yet still clings together. It is a planet swollen beyond reason but still intact, a living demonstration of physics pushed to extremes. Observations refine the picture with each passing year. Infrared maps trace the winds, ultraviolet spectra show gas loss, radial velocity curves confirm its mass. Transit timing variations reveal orbital decay, a clock ticking steadily toward destruction. Even the shape of its shadow is distorted, ingress and egress shifted by tidal stretch. Every photon of light becomes a clue, each measurement another piece of its story. WASP-12b is not an exception to the rules of physics, but a demonstration of them. It proves that migration is real, that inflation has multiple causes, that atmospheres can vanish under relentless radiation. It is a world once labelled impossible, now a cornerstone of exoplanet theory. It circles its star at impossible speed, swollen, fragile, and meticulously measured. A planet that shows us what happens when gravity, heat, and chemistry collide. Our next stop is LHS 3844b, a planet that sits just 49 light-years away in the faint constellation Indus, discovered in 2018 by NASA's TESS mission. Close in astronomical terms, it is near enough that the starlight we capture today began its journey when modern computers were already reshaping human life. The host is a red dwarf star, cooler and smaller than our Sun, yet ferocious in its proximity to the planet. Its orbit is tight, only 11 hours long, meaning this world circles its star faster than you can finish a single Earth day. The planet is a super-Earth, about 1.3 times Earth's radius and nearly twice its mass. Density is high, confirming it is built of iron and rock rather than gas. Infrared data from Spitzer showed no trace of an atmosphere, a finding that startled astronomers. The day side is scorching, nearly 770 degrees Celsius, while the night side falls below 250. Most worlds at such distance show at least a hint of air. This planet is bare. its surface exposed like a volcanic plain without a veil. The missing sky is a signal, telling us that red dwarf winds can scour atmospheres away completely. Silence is loud here because nothing protects the rock from the vacuum. The host star is active, prone to ultraviolet flares that batter nearby planets. An atmosphere must be thick to resist that assault, and even then, survival is uncertain. LHS 3844b had no such protection, or lost it quickly under the star's outbursts. Without air, the surface is locked into extremes, half fire, half ice. Think of a kiln burning in one room and an ice house beside it, with no doorway between. Heat cannot be shared, so one side glows and the other shatters into frozen stillness. The line between them is a terminator, a permanent border of shadow and twilight. There the contrast would be violent, though no air exists to soften it. Spectroscopy suggests the crust is dark, reflecting only 20% of incoming light. That low albedo is similar to basalt, the black volcanic stone of Earth's plains. The surface may be a fossil, a cooled lava field preserved for billions of years. Without erosion, it remains unchanged, a geological memory frozen in silence. Here lies the puzzle. A planet large enough to hold gas, yet stripped clean. Gravity should be strong enough to bind at least a light envelope. Even Mercury clings to a faint exosphere, a whisper of sodium and potassium. But this world is empty, its gases carried away into space. One answer is stellar wind, constant streams of particles that tear at atmospheres. Another is violent stellar flares, bursts of energy that bake and strip molecules. Together they leave a planet naked, unable to shield itself from ultraviolet light. This is the cost of orbiting close to a red dwarf. Theorists suspect it is a core, the inner skeleton of a once larger body. Perhaps it formed with a mantle of volatiles, only to lose them early. Perhaps migration carried it too near, where heat and wind devoured its sky. What remains is a fossilized heart, a monument to erosion on cosmic scales. Such erosion is not gentle, it is relentless across millions of years. Molecules gain energy, drift upward, and escape into space. When replenishment stops, the sky thins to nothing. The process ends with stone exposed, unshielded under constant radiation. Planets like this redefine our search for habitable systems. We once believed small red dwarfs could cradle life, offering long, stable lifetimes. Now we see their flares are too destructive, their winds too unkind. LHS 3844b is a warning, a reminder that not all stars are nurturing. The extremes are not only thermal, but spatial. On the day side, metals may glow, basalt softens, and heat radiates into blackness. On the night side, frost may condense, perhaps even carbon dioxide snow. The contrast is unforgiving, a planet divided in half. Astronomers study the light curve, measuring brightness drop as the planet transits. The depth reveals its size, while radial velocity provides the mass. Together they give density, the crucial clue to its composition. All three agree it is rocky, and yet different from Earth. Unlike Earth, it shows no evidence of plate tectonics or renewal. Its crust may be static, frozen under lack of water and air. The surface is ancient, a record left untouched. Where Earth remakes itself, LHS 3844b is silent. The lack of air removes every buffer against radiation. Cosmic rays strike directly, carving the surface chemistry. Any volatile is gone, evaporated long ago. The result is final, a barren core without disguise. Scientists sometimes call it a laboratory of extremes, with no clouds, no sky, the surface temperature can be read directly. The planet becomes a reference, useful for calibrating models of rocky exoplanets. Its clarity is rare because most worlds are shrouded. This makes LHS 3844b a teacher as much as an oddity. It demonstrates how atmospheres erode, how stars can sculpt their planets. It redefines our sense of habitability, forcing us to admit that mass alone is not enough. The true challenge is the environment, the star itself. A closer look at the host star shows its role. Red dwarfs are faint in visible light but violent in activity. They flare with ultraviolet power, far stronger than their size suggests. Planets nearby are doomed to suffer. Habitability here is a narrow window. Only distant orbits are safe, where winds weaken and radiation eases. Close worlds like LHS 3844b are sacrifices, stripped clean before they had a chance. They tell us red dwarfs may be poor hosts for life-bearing planets, yet this planet is important because it proves the point with clarity. Its atmosphere is absent, its rock revealed, its conditions extreme. No ambiguity clouds the data, no hidden gases confuse the picture. For once, the cosmos gave us a direct answer. Direct answers are rare in astronomy, a field of inference and patience. But LHS 3844b's silence is loud, impossible to misread. It leaves a planet both simple and complex, stripped yet profound. It is a message from the cosmos about survival. The message is that survival is fragile. Mass may be ample, yet winds can still win. Distance may be small, yet consequences are vast, and the result is emptiness, a world reduced to stone. Imagine standing at the terminator, the twilight band. Behind you, the horizon is lit, basalt glowing orange from endless day. Ahead, the plain is black, frost glittering under starshine. You stand on a world split, half boiling, half frozen. That division is not poetic, but real. Without an atmosphere, the contrast is sharp, unblunted. Every meter you step shifts temperature by extremes. The ground itself is a map of contradiction. Perhaps the planet once had volcanoes that fed a sky. Perhaps water flowed for a brief time in its early history, but flares would have erased those features swiftly. All that remains is a shell. This shell is an archive of erosion. It records what happens when gas is lost, but gravity remains. The planet endures as a witness to destruction. It survives only as stone. Theorists build models of escape using this case. They calculate how radiation drives loss, molecule by molecule. They compare densities to see what survives and what vanishes. In that process, LHS 3844b is a benchmark. Benchmarks matter because they ground speculation. Every new discovery is tested against them. If another stripped world is found, we compare it to this one. That comparison is power, refining the rules we teach, and so the planet is not a mistake. It is an example of possibility. It shows that stars can sculpt their companions into shapes we never guessed. It reveals the cosmos as restless. Restless is the right word for systems like these. They are not static, they are changing, carving planets anew. Every orbit is dynamic, a story unfolding under radiation and tide. Worlds here are forged, not preserved. If you step back, the larger truth emerges. Planets are not only born, they are remade. Atmospheres are temporary, skins that stars can peel away. What is left is a core, silent and dense. Cores like this remind us that Earth is lucky. Our atmosphere is shielded by magnetic fields and distance. Without those, our air would be gone. we too would be left bare. That comparison is not meant as fear, but as context. It shows how narrow the path of habitability can be. It shows why Earth is rare, even among billions of planets. And it shows why study of one world matters. Worlds like LHS 3844b are gifts. They reveal the limits of planetary survival. They sharpen our models of climate under alien skies, and they remind us that physics is unyielding. So this second stop is not less important than the first. It is central. It takes us from swollen gas giants to bare stone cores. It expands the definition of impossible, because here is a planet that persists without the cloak we expected. And in persisting, it shows us the universe is wider than our categories. Let's drift onward toward our third destination, because the story of strange planets does not pause. Each discovery is connected, each exception refining the map. The cosmos is patient, but it never stops surprising us. And LHS 3844b leaves us standing on the knife edge of contrast, fire to one side and ice to the other, wondering what waits beyond. Our next stop is K2141b, a rocky planet about 200 light-years away in the constellation Aquarius, first noticed in 2018 by the K2 mission of Kepler. Close to its star in a way that challenges our imagination, it completes a full orbit in only 6.7 hours. The host is an orange dwarf, a star cooler than the Sun, but proximity multiplies its energy until it becomes unbearable. At such a tight orbit, the planet is tidally locked, forever showing one face to its star and one to the void. The world is a super-Earth, roughly 1.5 times Earth's radius and 5 times its mass. Its gravity is strong, able to keep molten oceans from escaping too quickly into space. But the most astonishing feature is the burning day side, where rock does not stay solid. Instead, the crust is magma, a planet-wide ocean glowing orange and red. Rock here behaves like water on Earth, cycling between liquid, vapor, and solid. From the hot ocean, molecules evaporate, rising into an atmosphere made not of gases but of stone. Supersonic winds carry these vapors into the eternal night of the far side. There the vapors freeze, falling as mineral snow back onto the ground. This is the first known rock cycle on a planetary scale, a system where continents are oceans of lava and clouds are mists of silicate. The cycle is alien, yet it echoes Earth's familiar water cycle in form. On Earth, seas evaporate, clouds drift, and rain completes the circuit. Here, molten rock performs the same act under far harsher rules. The day side is scorching, reaching above 3,000 degrees Celsius. Iron, sodium, and silicon boil, leaving the crust to bubble and churn. The horizon is not blue, but orange, a haze of glowing vapor backlit by a merciless star. This side is a furnace, shaping the landscape into restless magma seas. Night-side conditions are the opposite, colder than 200 degrees Celsius. Here the ground is frozen, a desert where silicate snow falls from skies once filled with vapor. Darkness is absolute, broken only by the faint reflected glow of distant stars. The division between halves is sharp, a planetary scar with no twilight. Scientists call K2141b a lava world, but lava is too mild a word for what occurs here. Think of a river of molten stone stretching across a horizon without end. The surface is a restless ocean, stirred not by tides of water, but by heat itself. Winds are supersonic, fast enough to carry rock vapor halfway around the planet. Atmosphere on this world is a thin shroud of minerals, constantly being lost. Every second the star strips atoms, pulling them outward in a stream into space. Over billions of years the surface may erode, shrinking the ocean to hardened crust. But for now, the balance is active, rock still cycling between phases. The molten sea is not calm, but restless like boiling metal in a forge. Currents move beneath a glowing skin where crust forms and melts again. Waves of magma rise, peak and collapse, spraying fountains of silicate into the air. It is a dynamic surface, constantly reshaping under heat. The atmosphere is mostly silicate vapor, laced with sodium and calcium. As winds move, minerals condense on the night side, blanketing the ground. That snow is not water, but rock, powdered stone falling in slow flakes. Every flake is a message, proof of circulation on unimaginable scales. Imagine standing at the terminator, the dividing line between extremes. Behind you, the surface is a molten sea, glowing with unbearable light. Ahead is a plain of dark ice, frozen stone as brittle as glass. The air is filled with mineral mist, torn from oceans and delivered to the void. The cycle of stone resembles a planetary machine, always in motion. Heat drives evaporation, winds enforce transport, and condensation closes the loop. This machine is powered not by seasons but by relentless starlight. Its fuel is the very crust of the planet, stripped and recycled forever. Geology here is alive in a way we rarely consider. On Earth, we see volcanoes erupt, rivers of lava cut across landscapes. On K2 141b, every horizon is a volcano, every continent a mantle exposed. The planet is an eruption without pause. What defies models is the sheer persistence of such extremes. Close orbits should strip planets bare, yet this one remains. Instead of losing its surface completely, it has forged a cycle that maintains balance. That cycle is a lesson, showing survival even in violent proximity. The orbit is not only close, but permanent. Tidal forces keep it locked, always one face burned and one frozen. Rotation is synchronous, a rhythm unbroken by seasons. The star dictates every moment of the planet's existence. Astronomers measure the planet's light curve during transit. From depth, they extract the radius. From wobble, they find the mass. From those values, they compute density, a clear sign of rocky composition. Infrared mapping then revealed the stark contrast of hot and cold halves. Most planets reveal only hints, but K2 141b offered sharp data. Spitzer recorded a night side nearly airless, no thermal circulation to smooth temperatures. This means the atmosphere is thin, incapable of transporting enough heat, so the planet is divided, extreme halves without mediation. Models suggest that molten oceans may be thousands of kilometers across. Depth could reach hundreds of kilometers, magma stirred by currents beneath. At those depths, minerals separate, iron sinking while lighter elements rise. The mantle becomes a cauldron, constantly remixed by convection. Storms here are not made of water, but of rock vapor. Clouds of silicate dust may rise and drift, scattering light. The sky is not blue, but glowing with particulate haze. As winds roar, they deposit snow of stone across the shadowed side. This environment is a mirror of Earth's early history. 4 billion years ago, Earth too had a magma ocean during formation. Cooling eventually built a crust, water condensed, and life followed. But K2 141b is stuck, frozen in its molten youth. The permanence of its molten state is what defies expectation. Cooling should shrink oceans of magma, yet the star's heat keeps them alive. Every hour of radiation pours new energy into the crust. The result is an eternal foundry, never allowed to harden. Scientists compare this to a smelter left running without pause. Ore is melted, vaporizes, slag falls away. Instead of steel, the product is stability, a planet kept whole by recycling. The cost is a surface too violent for any life we know. Life here is impossible, not for lack of rock, but for lack of moderation. Chemistry is driven too hard, molecules torn apart before complexity emerges. Any organic compound would be destroyed in seconds. The world is a furnace, not a cradle, and yet its existence is meaningful because it expands the category of what planets can be. Before this, models assumed rocky worlds close to stars must vaporize entirely. Instead, we see one that is sustained by its mass and gravity keeping it intact. This shows the resilience of matter under extremes. Observations hint that the cycle may be imbalanced. Some vapors escape fully, lost into interstellar space. If so, the planet is slowly shrinking, losing layers grain by grain. But the process is slow, drawn out over billions of years. Time, therefore, becomes its sculptor, steadily trimming the surface. Each orbit is an act of erosion, each day a shedding of minerals. Yet the mass is large, giving it endurance against quick loss. This balance makes it a paradox, stable yet eroding. The paradox forces astronomers to revise their equations. Energy budgets must include lava cycles, not just gas. Escape velocities must include molecules heavier than hydrogen. Stars can strip not just skies but stones themselves. The image is that of a world where rock plays the role of water. Oceans are magma, clouds are silicate vapor, and rain is stone. It is a climate unlike any in our solar system. And it reminds us how varied planets can be. Planets like K2 141b were once unimaginable. Now they are data, measured and modeled in detail. Their very existence is a challenge, showing nature invents possibilities beyond our rules. Each one is a lesson, expanding our understanding. K2 141b's lesson is about resilience. It endures when nothing soft should endure. A body too hot to cool, yet too massive to dissolve. Its molten seas are eternal, flowing under a star that will burn for billions of years. And in that eternity, the planet remains trapped, cycling stone forever. The next planet in our list is known as HD 1T9733b, a planet that sits about 64 light-years away in the constellation Vulpecula, first discovered in 2005 when its shadow dimmed the light of its parent star. Close to its star, in the way of hot Jupiters, it completes an orbit every 2.2 Earth days. The host star is a K-type dwarf, cooler and dimmer than the Sun. Yet for this planet, it provides relentless radiation. At such a tight distance, the planet is tidally locked into showing the same face to its star at all times. The planet is a gas giant, slightly more massive than Jupiter, yet slightly smaller in radius. Its bulk is dense enough to resist the inflation seen in other hot Jupiters, but the atmosphere still stretches high. What draws attention most is its color, because telescopes have revealed it is a deep cobalt blue. The color is not from oceans or skies like Earth's, but from light scattering in a toxic atmosphere. Blue here is a warning, not an invitation. The color likely comes from silicate particles suspended high in the air. Those particles condense into droplets that form clouds of glassy rain. The winds drive that rain sideways at speeds exceeding 7,000 kilometers per hour. The atmosphere is a violent machine powered by starlight and rotation. On the day side, temperatures soar beyond 1,000 degrees Celsius, hot enough to vaporize many minerals. On the night side, the heat is still extreme because winds distribute energy in global circulation. The planet has no calm regions, only storms that never end. Imagine standing within that sky, if such a thing were possible. Around you, the air is thick with molten droplets, shards of glass driven at hurricane speeds. The ground never appears because there is no solid surface under gas giants. Beneath the atmosphere lies only more pressure, crushing deeper with each kilometer. Astronomers studied this world in detail using Hubble. Transit spectroscopy revealed the signature of sodium absorption, a clue to its composition. Follow-up studies suggested silicate clouds, explaining both the color and the scattering. Together, the results built an image of a planet ruled by glass storms. The winds are supersonic, reaching speeds far beyond Earth's jet streams. Heat from the star is absorbed on one hemisphere, then redistributed by gales that scream around the globe. The result is a planet where no side is quiet, even the night burns with stolen heat. Atmospheric models show an eastward jet, carrying the hotspot off-center from the star-facing point. Most hot Jupiters glow in infrared, but HD 1089733b shows sharper variations. Its emission spectrum is complex, with hints of carbon monoxide and water vapor. Yet water is not in the form of oceans or clouds, but vapor whipped into the winds. Even chemistry here is distorted by extremes. The rain itself is unlike any weather we know. Instead of liquid water, silicate droplets condense at high altitude. They fall as molten glass, swept sideways by storms before they can reach depth. Every flake is a razor, every storm a sandblaster made of crystal. Winds of this kind reshape the idea of atmospheric dynamics. On Earth, the strongest winds reach hundreds of kilometers per hour. On this planet, they exceed 7,000, faster than sound many times over. They carry heat, they carry dust, and they carry entire climates across hemispheres. The star itself is active, with flares and spots that affect measurements. This complicates data, but the planet's signals remain clear. Even under stellar noise, the absorption lines of molecules stand out. The planet remains a textbook case of extreme weather. Clouds on HD 1189733b are not gentle veils, but thick hazes of silicate particles. They scatter blue light, producing the cobalt hue seen by Hubble. Unlike Earth's Rayleigh scattering, this is scattering from mineral dust. The resemblance to Earth's blue sky is misleading, a trick of physics in hostile air. The atmosphere may extend far into space, forming a tail. Ultraviolet observations revealed signs of atmospheric escape, hydrogen streaming outward. This makes the planet a slow evaporator, shedding mass under stellar winds. It may not last forever, but for now it is a survivor. Survival here means maintaining balance between gravity and radiation. Gravity holds gases in, while heat tries to lift them out. So far, gravity wins, but the star is loud, pressing always against the edges. Over eons, the planet may shrink, losing layers as the cycle continues. Interior models suggest a core, heavy and rocky beneath layers of gas. Above it lie mantles of hydrogen and helium, thick and crushing. Temperatures rise with depth, pressures climb beyond imagination. There is no clear boundary, only a gradient into the unknown. Unknown defines much of what we say about HD 18973-3b. We do not know the exact chemistry of its storms. We do not know how deep the silicate clouds reach. We only know the violence is real, recorded in light curves and spectra. The storms are constant reminders of how alien planets can be. Where Earth has gentle seasons, this planet has permanent chaos. Where our rain is water, here it is molten glass. Where our winds are mild, here they are supersonic gales. Scientists see this as a laboratory for physics under stress. Wind, heat, and chemistry interact in ways impossible on Earth's surface. Simulations must include feedback between radiation and motion, a difficult task. Each new observation forces equations to adapt. The lesson is that even familiar categories like hot Jupiters are not uniform. Some are swollen and inflated, others are compact. Some are cloudy, others clear. And some, like HD 118973-3b, are violent beyond our first theories. Violence here is sustained, not brief. Storms are eternal, locked to the rhythm of the orbit. Heat is constant, driven by proximity that never changes. Nothing about this world is gentle. The cobalt blue color is a trap for the imagination. At first glance, it looks like Earth, a world of seas and skies. But that similarity is false because its seas are fire and its skies are glass. Beauty here is lethal, a reminder that color is no guarantee of comfort. Comfort is absent at every scale. Temperatures burn high enough to melt steel. Winds shred particles into microscopic blades. Rain is not cleansing but cutting, a storm that scours. This makes HD 118973-3b a paradox. It is familiar enough in size and category, yet alien in experience. It orbits a star not unlike our own, yet the outcome is opposite. It is both ordinary and extraordinary, depending on your angle. Angle matters in how we detect it too. Transits reveal size, radial velocity gives mass. Spectra uncover chemistry, colors reveal scattering agents. Each piece of data builds a layered portrait. That portrait is not static because atmospheres are dynamic. Glass clouds shift, winds evolve, and circulation changes with time. Repeated observations reveal variability, a weather pattern without calm. The planet is always in motion, never at rest. Motion defines its destiny as well. Orbiting so close, it is doomed to slow decay. Tidal forces extract energy, shrinking its path gradually. In millions of years, it may fall, consumed by its star. The timescale is long, but the warning is short. Planets so close to their stars cannot last. They are temporary, transient features in cosmic history. Their presence is both real and fragile. Fragility is hidden by the power of its storms. It looks eternal, yet its fate is sealed. The same star that feeds its chaos will one day end it. Its story is both fierce and finite. And still, HD 118973-3b is a teacher. It tells us to expect climates stranger than our dreams. It proves that beauty may conceal hazard. It demonstrates that planets are restless, varied, and unpredictable. The story of HD 118973-3b continues with ongoing measurements. Future telescopes will map its atmosphere in detail. They will trace winds, track chemistry, and follow escape. Each year adds to the picture, sharpening our view of chaos. Chaos is not failure, but truth. The cosmos is not tidy, it is untamed. HD 118973-3b is proof that planets are not bound to Earth's rules. They are bound only to physics, which allows more than we imagined. Our next stop is Gliese 436b, a planet orbiting a faint red dwarf about 33 light-years away in the constellation Leo, discovered in 2004 by radial velocity methods and later confirmed by transit. Close to its star, the orbit takes just 2.6 Earth days, a rapid cycle that keeps the planet locked in perpetual day and night. The host star is dim, radiating less than a third of the sun's light, but its proximity makes the planet far hotter than intuition first suggests. At roughly Neptune's size, the world carries a puzzle that defies every expectation of planetary physics. The radius is similar to Neptune, but the mass is heavier, producing a density that is surprisingly high. That density is strange because the surface temperature of 700 degrees Celsius should have boiled away light gases long ago. Instead, the planet remains stable, an object with hydrogen, helium, and water locked into states unknown on Earth. It is this combination that earned it the name of a world made of burning ice. Ice in this context does not mean frozen cubes of water in a glass. It refers to exotic crystalline phases of water that can exist under pressures far beyond Earth's oceans. Deep inside the planet, molecules are compressed so tightly that they form solid lattices even at high temperatures. Those lattices remain solid while the environment around them burns. The paradox of Gliese 436b is that water can be both frozen and hot. On the surface, heat drives chemistry into extremes, producing fire where volatiles would normally evaporate. Yet beneath the crust, the water remains locked, immovable under gravity's grip. The result is burning ice, a phrase that captures the contradiction. Most Neptunes close to stars are expected to swell, becoming puffed gas giants with low density. Gliese 436b is the opposite. Compact, dense, and stubborn. It holds onto gases with surprising strength, showing no signs of runaway loss. Its gravity is a warden, keeping even hydrogen chained in place. The atmosphere is enriched with hydrogen, but models suggest far less than Neptune carries. This implies it has been eroded and stripped over billions of years, but not entirely. What remains is a thin but powerful shell, trapping heat and altering the spectrum. Astronomers call this a sign of unusual chemistry, a balance not found in our system. Observations from Hubble revealed the atmosphere contains methane, carbon monoxide, and likely water vapor. But the ratios are wrong compared to Neptune, showing disequilibrium. Instead of water vapor dominating, carbon monoxide is abundant. This indicates that high heat drives reactions toward unexpected outcomes. At 700 degrees Celsius, the upper atmosphere is a furnace. Molecules are broken apart, radicals recombine, and chemistry is reset. Circulation carries heat around the globe, making the night side still hot. The entire climate is locked in combustion-like equilibrium. Burning here is metaphorical, but accurate to the violence of the chemistry. Water cannot boil away because gravity holds it in ice phases deep below, but gases at the top still fry, breaking into new forms. The system is a laboratory of fire and solidity combined. The presence of exotic ice phases is a prediction from models. On Earth, we know ice-E, the common form. But at high pressure, water creates ice-7, ice-X, and other dense structures. These phases are stable, even at thousands of degrees. Pressure forces water into these crystalline cages. At millions of atmospheres, molecules cannot move freely. Even heat that would vaporize oceans on Earth cannot free them. So water remains a solid, but glowing from the heat around it. This is why astronomers describe Gliese 436b as burning ice. It holds fire and ice together, contradictions fused into one. The term is not poetry but physics, a necessary label for impossible matter. It is a demonstration that nature outruns language. Language struggles to capture what lies inside. Imagine a core wrapped in hot crystalline water. Imagine an atmosphere of hydrogen, fire, still bound at extreme heat. The image is both familiar and alien at once. This world is thought to be a remnant of a larger planet. Perhaps once it was closer to a Neptune or even a Jupiter. Over time, the star stripped away lighter gases, leaving a denser shell. What remained is compressed water held as burning ice. Migration may also play a role. The planet could have formed farther out, gathering more volatiles in a colder region. Later, it drifted inward, drawn by disk interactions or orbital nudges. Its final location is a place of erosion, not birth. Models of escape predict that hydrogen should vanish quickly. Yet this world retains enough to alter its spectrum, a contradiction. Perhaps magnetic fields help shield it, a layer against stellar winds. Or perhaps gravity is simply too strong for quick loss. Loss is evident in one way, however. Hubble detected a massive tail of escaping hydrogen, like a comet. This shows the atmosphere is bleeding, slow but steady. Even as the core holds water, the sky is shedding. The comet-like tail is an image of fragility. It proves that the planet is not eternal. Given billions more years, the atmosphere may vanish. What will remain is only the icy skeleton. That skeleton would still be strange, still dense. A body of hot crystalline water, stripped of gas. Such a world would be a super-Earth of solid ice rock. It would circle its star as a ghost of loss. Ghosts like these remind us that planets evolve, they are not fixed. Gliese 436b is in the middle of transition. It shows us a world caught between Neptune and super-Earth. It is an intermediate stage in planetary history. The contrast with Neptune is sharp. Neptune is cold, blue, and stable. This world is hot, red dwarf lit, and unstable. Yet both are roughly the same size. Size deceives because density and chemistry tell the truth. Two planets of equal radius can be entirely different. One may be gas and ice, the other rock and iron. Gliese 436b is a reminder of that lesson. Lesson here is about pressure. We think of ice as fragile, but under gravity it is unyielding. We think of heat as destructive, but under confinement it is contained. The paradox is that confinement creates stability. Stability is temporary in cosmic time. Erosion continues, the tail of hydrogen lengthens. The atmosphere thins as molecules escape. Eventually, the planet will be a stripped core. Even so, the present is unique. Right now, the world balances between loss and retention. It shows us exotic matter, impossible phases in real environments. It forces us to expand definitions of ice, fire, and planet. Planets like this are not failures, they are discoveries. They show that theory was narrow. They remind us to keep models flexible. They prove that the cosmos is always creative. The phrase burning ice captures imagination, but the reality is deeper. Exotic phases are real, tested in laboratories with diamond anvils. Those experiments confirm that Ice 7 can exist at thousands of degrees. So the physics of Gliese 436b is not fantasy, but fact. Fact is powerful when paired with beauty. This world is not beautiful in any gentle sense. It is beautiful as proof of nature's capacity. It is beautiful as a challenge. Challenge is what drives astronomers to observe. They refine spectra, look for chemical lines. They model circulation and escape. They debate how such a world could survive. The answer is still not complete. Perhaps magnetic fields slow erosion. Perhaps the mantle is denser than we guess. Perhaps migration history is more chaotic. Chaos is often the missing piece in planetary systems. Gliese 436b may have been tossed inward by neighbours. It may have lost siblings in orbital wars. It may have landed here by sheer luck. Yet its survival is ordered in its own way. The ice remains solid, the orbit remains stable. It continues its cycle, circling every 2.6 days. It continues to shine as a paradox of matter. Matter defines the story here, not metaphor. This is water in forms unseen, hydrogen in escape, carbon monoxide in dominance. It is not Earth, Neptune, or Jupiter, but an intermediate. It is what happens when planets are pressured beyond our categories, and so Gliese 436b is another world with no right to exist. It defies the rules of heat and phase. It maintains ice under temperatures of fire. It forces physics to explain, not dismiss. Explanation is ongoing because telescopes will look again. The James Webb Space Telescope already has plans to examine it. High precision will uncover new molecules. We will soon learn how deep the burning ice runs. The next world we're heading towards is Kepler 7b, a planet discovered in 2009 by the original Kepler mission, orbiting a star nearly 3,000 light-years away in the constellation Lyra, close to its parent star with a period of just under 5 Earth days. It receives more radiation in that time than Jupiter does in an entire year. The host star is slightly larger and hotter than the Sun, a star that gives off a steady blaze of light strong enough to sculpt its planets into extremes. Kepler 7b, however, refuses to match expectations because its bulk is puffy beyond reason. The radius of Kepler 7b is about 1.6 times that of Jupiter. Its mass, though, is only about half that of Jupiter, a contrast that makes its density one of the lowest measured. At just 0.1 grams per cubic centimeter, it is less dense than styrofoam. Astronomers call such worlds superpuffs, planets swollen to impossible dimensions. Most gas giants close to stars are dense, compact, and compressed by heat. Kepler 7b is the opposite, swollen, light, and balloon-like. This contradiction makes it a planet with no right to exist. Its presence forces astronomers to refine every model of inflation. The word inflation describes a planet's tendency to swell under heat. Energy from the star can be absorbed in the atmosphere, slowing cooling. Ohmic heating from currents, tidal flexing, or opaque molecular blankets all contribute. But Kepler 7b is more inflated than these processes predict. Clouds may provide the answer because Kepler 7b is highly reflective. Observations with Kepler revealed an unusually bright albedo, about 50%. That brightness implies clouds of exotic composition high in the atmosphere. Minerals such as N-startite or perovskite may act as reflective mirrors. The atmosphere is likely layered with silicates, forming thick reflective sheets. Those sheets scatter starlight back into space, reducing absorption. Yet paradoxically, the planet still swells, its radius inflated far beyond reason. This leaves us with a mystery still unsolved. Mystery deepens when we examine thermal data. The dayside temperature is about 1500 Kelvin, not the highest among hot Jupiters. Still, that should not inflate the planet so extremely given its mass. Something additional must be feeding energy into the interior. Interior models struggle to match both size and mass. A core would normally compress the gas, but here the core seems minimal. The envelope dominates, leaving the planet fluffy. Kepler 7b is a balloon, gas stretched thin over volume. Imagine holding a balloon filled not with air but with fog. The balloon is large, yet lighter than you expect to lift. Kepler 7b is such a balloon, orbiting with impossible grace. It is a cloud disguised as a planet. Planets like this are fragile. The atmosphere is barely bound, vulnerable to erosion. Starlight presses, winds lift, hydrogen escapes, and yet the planet still survives. Its survival is a lesson in balance. Gravity holds just enough, while starlight inflates without breaking. Each day, the tug-of-war continues. The result is a paradox visible in light curves. Light curves showed not only transit dimming, but phase variations. The brightness shifted with orbital phase, implying reflective clouds. This was one of the first planets where cloud maps were attempted. Astronomers built the first weather portrait of an alien world. Portraits revealed patchy brightness on one hemisphere. The west side was more reflective, covered in dense clouds. The east was darker, perhaps clearer. Thus we saw the first planetary climate outside our solar system. The idea of mapping another planet's clouds was once absurd. Now it is normal, thanks to Kepler 7b. By measuring subtle light shifts, we glimpse alien skies. This planet is not only strange, but also a pioneer. Pioneer worlds redefine our categories. Kepler 7b is one of the original superpuffs, showing that gas giants can be larger and lighter than expected. Its density is lower than wood, lower than cork. It challenges the word planet itself because it feels like a drifting balloon. The orbit is stable but close. 5 days means constant irradiation. The same face is always turned to the star. Tidal locking enforces eternal day and night. Day is reflective and bright, the side we measure. Night remains hidden, cooler but still hot by Earth standards. Heat is transported by winds, though unevenly. The result is a climate with strong east-west contrasts. Contrast is key to its puzzle. If reflective clouds dominate, why is the radius still inflated? If energy is reflected, less heat should be absorbed, yet the inflation is still excessive. Excess points to internal heating. Currents induced by winds create ohmic heating. Charges interact with the magnetic field. Energy is pumped inward, inflating the planet. This mechanism is not unique, but Kepler 7b shows it most extreme. The balance between reflection and heating is delicate. Too much reflection reduces swelling, too much heating expands. Kepler 7b balances on that line. Line between survival and escape defines its atmosphere. Escape velocity is low, gases are loose. Hydrogen and helium rise, molecules leave, but gravity still pulls enough to retain. Retention is temporary on cosmic scales. Over billions of years, gases will bleed. The planet may shrink into a denser core. Today, though, it remains a swollen giant. Giant is the right word, but hollow. It has the radius of a colossus, but the mass of a dwarf. This mismatch is the root of its mystery, a contradiction made visible by light. Light is our only tool, yet it is enough. Transits reveal depth, radial velocities give mass. Brightness variations map clouds. Together they give a story of puffiness. This story is unfinished because models still fail. None perfectly match both radius and reflectivity. Perhaps unseen factors still work. Perhaps opacity is higher than assumed. Opacity traps heat, slowing cooling. Minerals or metals may block radiation. The interior cannot shed energy. The result is swelling, a planet too large. Large but fragile, Kepler 7b reminds us that gas giants are not all alike. Some are compact, some are inflated, some are clear, some cloudy. Nature builds every possible combination. Combination here is reflection and inflation. It reflects half of starlight yet swells like a furnace. It shows clouds do not always cool. Sometimes clouds help a planet grow. Grow in this sense means swelling, not accretion. The planet has stopped gaining mass, but it has gained volume. It is a paradox of expansion. Expansion challenges our categories of habitability, not because Kepler 7b is habitable, but because models of atmospheres must expand. If this world can exist, others may be even stranger. The cosmos is never finished with surprises. Our next stop is CoRoT 7b, a planet discovered in 2009 by the French-led CoRoT mission, orbiting a star about 490 light-years away in the constellation Monoceros. Close to its parent star in a way that staggers the imagination, it circles once every 20 hours, faster than a single Earth day. The host is a G-type star similar to the Sun, but the proximity transforms its light into a furnace. CoRoT 7b became the first confirmed rocky exoplanet, and its surface is nothing like the Earth that word suggests. The planet is about 1.6 Earth radii, but 5 times as massive. Its density is high, nearly identical to Earth's, confirming a composition of rock and iron. Yet the closeness to the star forces temperatures above 2500 Celsius on the day side. At such levels, stone itself turns to liquid. Lava is the landscape here, an endless magma ocean that stretches across the day hemisphere. There is no soil, no sea, no solid ground as we know it. Waves of molten rock rise and collapse, driven by constant radiation. The horizon is aglow, an orange sea under white starlight. The planet is tidally locked, always showing one face to the star. The day side is fire, but the night side is far colder, likely below 200 Celsius. Without an atmosphere to move heat, the contrast is extreme. One hemisphere is a burning ocean, the other a frozen desert. Imagine standing on the line between day and night. Behind you, lava seethes under unbearable heat. Ahead, the ground is brittle rock, cracking under cold silence. The transition is a knife-sharp boundary only kilometers wide. Astronomers call CoRoT 7b a lava Earth, a world where continents are seas of molten stone. Its atmosphere is thin, made only of vaporized rock. Silicates and sodium evaporate, forming mineral mists above the lava. Winds may carry those vapors to the cold side where they snow down as stone. This creates a mineral cycle, rock evaporating on the hot side, drifting and condensing on the cold. It is a mirror of Earth's water cycle, but made of silicate instead of water. Rain is not liquid, but stone, falling as crystals from alien clouds. Each flake is a frozen fragment of lava returned to the ground. Most planets that close to their stars are gaseous, stripped of rock long before stability. But CoRoT 7b is dense and rocky, enduring where others fail. Its mass is too great to evaporate entirely, too heavy for winds to erase, so the planet remains a core, iron and rock against starlight. The orbit is tight, one of the closest known. At only 0.017 astronomical units, it is 20 times nearer than Mercury is to the Sun. The star fills a massive portion of the sky, dominating every horizon. Its light is the planet's defining force, sculpting every feature. Force is also tidal, pulling constantly at the interior. The crust may flex, feeding volcanoes with endless heat. If eruptions occur, they feed the thin atmosphere, but most of the surface is a stable sea of magma. Surface is an incomplete word here. Beneath the ocean lies mantle and iron core. The crust is only molten skin, glowing with convection. This is geology without pores, a planet in permanent eruption. Geology here is a furnace. There are no mountains, only waves of molten stone. There are no rivers, only magma currents. Every horizon is an inferno, every vista hostile. The discovery of CoRoT 7b was a milestone. It proved that rocky planets exist outside our system. It opened the category of terrestrial exoplanets. But the first example was a world made of fire. Fire dominates its chemistry. Silicate molecules split, metals rise into vapor. Spectra show signatures of sodium and potassium. Each line is proof of stone turned to gas. Gas here is temporary, blown away by winds. The star strips molecules, sending them into space. Still, the surface feeds the atmosphere each second. A steady exchange keeps the thin veil alive. The atmosphere is not protective. It cannot shield from radiation or flares from the star. It is only a transient layer, a reflection of the surface below. The planet is naked to cosmic light. Light from the star is overwhelming. It bathes the surface in heat beyond endurance. Even iron would melt, even steel would vaporize. The crust is a liquid mirror of fire. Astronomers modeled its interior to test survival. They found it could not escape erosion entirely. Hydrogen and helium were long ago lost, but the rocky skeleton remains bound. Bound tightly by gravity, it endures. Its orbit is shrinking slowly from tidal forces. Transit timing variations may show orbital decay. One day it may fall into its star. The timescale is millions of years, not long by cosmic standards. Its end is certain, though still far in the future. For now, it is a burning monument to close in survival. It is a defiance of expectation. Expectation once said rocky planets could not orbit so close. Now we see they can persist. Theorists must account for their formation. Migration and tidal capture may be answers. Answers point to birth farther out. The planet may have formed in the cooler disk. Then it was drawn inward, orbit by orbit, pulled by the gas. It stopped only when tides locked it in place. Place here is hostile. The habitable zone is far away. This world is no cradle, but a burning anvil. It shows what stars can forge from rock. Forge is not metaphorical, it is literal. The surface is melted like ore in a furnace. The air is a plume of metallic smoke. The cycle is endless planetary smithing. The comparison with Earth is striking. Earth balances water, air, and life. CoRo T7b balances lava, vapor, and loss. One is temperate, the other extreme. Extreme does not mean unworthy of study. It means valuable as a teacher. It tells us that rocky planets are not always Earth-like. They can be molten, barren, and still stable. Stability comes from mass. Even stripped of gases, gravity holds. The planet remains compact and dense. It continues to circle without fail. The radius and mass define its identity. It is not Neptune, not Jupiter. It is Earth-like in size, but not in spirit. It is a planet of endless fire. Fire has become its permanent state. There is no cooling, no night to balance. The crust is kept in constant motion. It is a fiery ocean without shore. Imagine the skyline of such a world. Instead of clouds, there are plumes of silicate. Instead of seas, there are glowing waves of rock. Instead of night, there is only dim glow. This image is not poetic only, it is supported by models. Simulations show magma oceans on close-in worlds. Temperatures fit observed light curves. The data confirms a lava landscape. Curves from transit photometry revealed its radius. Radial velocity gave its mass. Density calculations confirmed it is rocky. Infrared mapping confirmed its heat. Heat is the essence of its existence. The planet is heated by both light and tides. tidal flexing adds to the furnace. The result is a never-ending magma ocean. This ocean circulates like a sea. Convection drives molten currents. Denser material sinks, lighter floats. The ocean is geology in permanent motion. Motion extends to the atmosphere. Vaporized rock rises, then falls as stone rain. The cycle is alien but predictable. It is weather made of stone. Stone rain may blanket the night side in dust. Crystals accumulate in frozen fields. The dark side is littered with fallen minerals. It is a desert of silicate snow. Snow of this kind is violent. It is sharp, crystalline, and hard. Instead of melting, it shatters into fragments. The night side is a land of frozen blades. Blades of stone are the opposite of our gentle snow. They carve, they grind, they pierce. But on Coro T7b, there is no one to see. The snow falls into empty silence. Silence is the companion of every extreme world. No air carries sound. No winds whisper except in mineral haze. The only voice is molten boil. Boil is the constant surface action. Lava bubbles and bursts. Vapors rise, condense, and fall. It is a closed cycle of fire and stone. Our next stop is 55 Cancri E, a super-Earth orbiting just 40 light-years away in the constellation Cancer, discovered in 2004 as one of 5 planets circling its star. Close does not capture its nearness because this planet completes a full orbit in just 17.7 hours. The host star is slightly brighter and hotter than the Sun, a G-type dwarf that dominates the sky of its planets. 55 Cancri E is the innermost world, and its nature has defied every rule we once trusted. The planet is about twice Earth's radius and 8 times Earth's mass. That makes it a true super-Earth, a rocky giant compressed under gravity. Yet its density does not match ordinary rock, suggesting unusual chemistry. For years it has carried the name of the Diamond World. Diamond here refers to the possibility of carbon dominance. If the planet formed in a carbon-rich disk, its interior could be filled with graphite and diamond. Under pressure, carbon would crystallize deep within the mantle. The result would be a world sparkling with compressed carbon. The surface, however, is not sparkling. At over 2,000 degrees Celsius, it is likely an ocean of molten lava. Infrared mapping reveals thermal hotspots that shift unpredictably. Sometimes the heat is centered, sometimes it is offset. Offset patterns suggest volcanic activity. Jets of gas may vent from below, driving circulation. This makes the planet a restless volcano, erupting across a hemisphere. Its surface is an ocean of fire and stone storms. Astronomers call it a lava world, but not in the simple way of Coro T7b. Here the atmosphere is not absent, but struggling. Spectra suggest a volatile envelope, perhaps rich in carbon monoxide or nitrogen. That envelope is thin, constantly stripped by the star. Stripped atmospheres leave tails, and some observations hint at escaping gas. The planet is losing molecules at a steady rate. Each orbit bleeds more material, eroding the fragile layer. Yet enough remains to affect the surface climate. The climate is unstable, with nightside heat higher than models expect. Winds or magma flows may carry energy into darkness. Perhaps the atmosphere redistributes heat. Perhaps volcanic activity adds its own glow. Glow is the striking detail because phase curves reveal the planet shines. It is not reflective like Kepler 7b, but emissive. It radiates infrared light, heat pouring out of the surface. This glow proves that molten rock is present. Most super-Earths are assumed to be rocky and solid. 55 Cancri E is rocky but fluid, a core exposed to extremes. It challenges our picture of terrestrial planets. It is not Earth-like, it is Earth magnified. The The day side is hotter than molten steel. The night side is cooler but still above 1000 Kelvin. This contrast is small compared to lava worlds without air. That implies the presence of some circulating atmosphere. Atmosphere here is exotic. Not nitrogen and oxygen, but carbon monoxide and hydrogen. Not water vapor, but silicate gas. Not clouds of water, but mineral hazes. The host star is bright and close. Its radiation bathes the planet in constant flux. Any atmosphere is ionized, molecules split. The star sculpts the air as quickly as it is made. Made, again by volcanic release, the gases come from below. As magma oceans churn, volatiles rise. They escape through cracks, feeding the thin veil. The planet is recycling itself into its own air. This is why scientists compare it to Io, Jupiter's volcanic moon. But Io is small, cold, and distant. 55. Cancri E is vast, hot, and close. It is Io magnified to planetary scale. Scale is the marvel here. A super-Earth of 8 Earth masses should be stable. Instead, it is unstable, volcanic, and restless. It should be solid, but it is fluid. Fluidity makes its surface a cauldron. Magma flows replace rivers. Eruptions replace mountains. The crust is a restless ocean. Ocean here does not mean water. It means molten silicate stretching horizon to horizon. The lava may be hundreds of kilometers deep. Its currents churn in convection cycles. Convection carries heat, moving plumes. Plumes rise, crust breaks, magma erupts. The cycle is endless, a restless planetary heartbeat. Each eruption changes the face of the world. World is the right word, but alien. No biosphere softens its surface. No oceans cool its heat. It is a world of naked planetary force. Force defines its orbit too, a near-death spiral. Tides pull constantly, sapping energy. The orbit may decay, the planet may fall, but for now it remains in fiery balance. Balance is deceptive because the atmosphere betrays instability. Infrared data shows variability, heat shifting over months. This implies ongoing change. It is not static, but dynamic. Dynamic systems defy easy theory. Some models predict a thick atmosphere. Others predict none, only magma. The truth is in between, a mixed state. State of matter here is blurred. Gas, liquid, and solid coexist in molten cycles. Rock vaporizes, condenses, and rains as stone. The planet is a mineral storm. Storms of rock are alien to our imagination, but phase curves demand such motion. They show redistribution of heat. They reveal constant atmospheric change. Change forces us to confront carbon theory. Some argue the planet is carbon-rich, forming diamond deep below. Others argue oxygen dominates, leaving no diamond. The truth may depend on disk chemistry. Chemistry of birth sets destiny. If carbon exceeded oxygen, diamond forms. If oxygen exceeded carbon, silicates dominate. Both are possible, both are plausible. Plausible but unconfirmed. The diamond world remains a maybe. Still, the idea has captivated public imagination. A planet worth quadrillions in diamond value is a powerful story, but science is more cautious with that label. Label aside, the strangeness is real. 55. Cancri A is unstable, molten, and volatile. Its heat is permanent, its air is temporary. It is a planet in perpetual flux. Flux defines its story. Flux of gases rising, flux of magma circling, flux of radiation stripping, flux of orbits decaying. It is a restless object, never in equilibrium. Equilibrium is impossible this close to a star. Energy input is relentless, outflow cannot match. The planet swells with heat, It glows as a world in constant burn. Burn is not combustion, but exposure. The crust is melted, the mantle venting. The surface is hotter than a furnace. It is a burn of planetary matter. Matter deep inside may still hold secrets. If carbon is abundant, diamonds form. If oxygen dominates, exotic rocks form. Either way, the core is extreme mineralogy. Mineralogy at this scale is a clue to origins. Did it form in place or migrate? Did it start larger, losing outer layers? Each option is still on the table. Table stakes are high for theory. This planet challenges models of rocky super-Earths. It shows surfaces can be volcanic oceans. It shows atmospheres can be mineral veils. Veils of gas hide and reveal by turns. Observations show shifting patterns. Sometimes spectra show volatiles, sometimes they fade. The atmosphere may wax and wane. Wane is consistent with volcanic eruptions. Outgassing produces temporary air. Stripping removes it within months. The cycle repeats, unstable breathing. Breathing of a planet is not life, but geology. This world breathes gases from molten lungs. It exhales rock vapor. It inhales stellar winds. The result is a flickering atmosphere. Atmosphere is key to its mystery. Without it, the night side should be colder. With it, heat redistributes, raising temperatures. The data supports the latter. Temperatures still define neat models. They change from year to year. No exoplanet should vary so quickly. This one does, leaving astronomers puzzled. Puzzle is what defines 55 Cancri E. It is rocky but volcanic, stable but eroding. It is carbon-rich, yet silicate-dominated. It is both diamond and lava. Lava dominates the view we can confirm. Diamonds may exist only in theory. What is certain is molten surface. What is certain is planetary violence. The next world in our list is WASP 76b, a planet orbiting nearly 640 light-years away in the constellation Pisces, discovered in 2016 by the Wide-Angle Search for Planets survey. Close to its host star, with a period of just 1.8 Earth days, it receives more radiation in a single orbit than Jupiter receives in a lifetime. The host star is an F-type subgiant, hotter and larger than the Sun, flooding its inner system with light. At this proximity, the planet is locked in permanent day and night. The planet is a hot Jupiter, similar in mass to Jupiter but far more inflated. Its radius is almost twice that of Jupiter, a swollen balloon of gas. Density is extremely low, about a quarter that of water. It is less compact than wood, yet survives close to a raging star. Day-side conditions exceed 2400 degrees Celsius, enough to vaporize iron. In this furnace, metals become gas. Iron atoms rise into the atmosphere, carried into high winds. The circulation drives them toward the night-side sky. On the night side, temperatures are far cooler, though still above 1000 Celsius. Here, iron vapor condenses. Droplets form and fall, producing rain made of metal. The weather forecast is permanent iron storms. Imagine standing under that rain. The air is thick with iron mist glowing in the dim starlight. Droplets fall as molten metal, sizzling as they strike invisible layers below. There is no safety, only a horizon of metallic clouds. Clouds here are not of water, but of vaporized minerals. Spectra reveal sodium, calcium, and titanium oxide, but iron is the element that leaves the strongest signal. Its absorption lines cut clearly through the stellar light. Light is our only window, and it reveals extremes. Hubble and espresso spectrographs confirmed iron vapor. They traced it across the limb from day to night sides. They saw the pattern of rain in chemical shadows. Shadows in spectra are fingerprints of molecules. Each element absorbs at a specific wavelength. Iron's signature is unmistakable, a sharp cut in the spectrum, so the conclusion is certain: iron falls. The night side is a land of endless precipitation, but the day side never knows rain, only searing gas. This contrast makes the planet deeply asymmetric. It is one world divided by temperature. Most hot Jupiters show circulation that smooths heat. WASP 76b shows circulation that moves chemistry. Heat alone is not redistributed, but iron itself is transported. The weather is a cycle of vapor and rain. Rain of iron is no metaphor. At thousands of degrees, iron boils. At cooler nightside levels, it condenses and falls. The cycle repeats every single orbit. Orbit here is swift and relentless. 1.8 days means the planet is grilled. Its atmosphere is never at rest. Currents race faster than any Earth storm. Storms on Earth carry water at hundreds of kilometers per hour. On WASP 76b, winds reach thousands. They roar across hemispheres, dragging metals with them. This is weather beyond earthly comparison. Comparison with Jupiter shows the difference. Jupiter's storms are cold, colored by ammonia clouds. WASP 76b's storms are hot, driven by iron vapor. The scale is similar, but the chemistry is alien. Alien here does not mean life, but unfamiliar physics. The same rules of condensation and rain apply, but the materials are exotic, iron instead of water. This shows weather is universal, but variable. Variable too is the brightness. Phase curves reveal shifts in emission. The hottest spot is offset from the substellar point. This proves winds carry heat in jets. Jets are supersonic, stronger than anything on Earth. They transport iron across the terminator. They balance temperatures but only partially smooth them. Nightside remains cool enough for rain to form. Dynamic models predict complex clouds. Silicate and iron form reflective layers. These clouds scatter light, altering albedo values. WASP 76b shines faintly with mineral haze. Haze is confirmed by muted spectra. Instead of sharp lines, many are blurred. This implies clouds obscure direct view. The planet hides its furnace under mist. Mist of iron, however, cannot hide entirely. High-resolution spectra still find its trace. The detection was hailed as a first, proof of iron rain. This gave WASP 76b its unique identity. Identity matters in exoplanet science. Each new detection expands the category of possible. Before this, iron rain was only theory. Now it is observed, a measured reality. Reality is even stranger than expectation. The planet's density is low, yet it endures. Inflation makes it swollen, yet not destroyed by erosion. It is fragile, yet lasting. Lasting for now, though tides may erode the orbit. Close-in hot Jupiters often face orbital decay. Energy bleeds, the orbit shrinks, the star consumes. But millions of years may pass before its end. End or not, its present is astonishing. A climate where iron is weather, where metals fall as rain. A place where the word storm means something harsher. A place that shows planets can be truly alien. Alien weather reminds us not to assume Earth's logic. Our water cycle is only one version. On other worlds, other materials perform the cycle. Here, iron takes water's role. Role reversal makes the familiar strange. Rain is metal, clouds are stone, and skies glow orange. Heat fuels winds. Winds fuel chemistry. Chemistry fuels storms. The pattern is recognizable but twisted. Twisted into extremes, the cycle pushes imagination, but it is also solid science. The data is consistent, the physics sound. The result is an atmosphere unlike any we expected. Expected worlds were once neat: gas giants, rocky planets, icy dwarfs. Now we see planets with iron weather. We see lava oceans and burning ice. We see systems that force theory to stretch. Stretch is what science must do. It bends to fit evidence. It learns from contradiction and surprise. WASP-76b is both contradiction and lesson. Lesson here is that no chemistry is off limits. If temperature and pressure align, iron will reign. If dynamics allow, winds will carry. If cooling occurs, droplets will fall. Fall, they do, endlessly, invisibly to us, but real. Molten iron splashes into deeper layers. There it merges, circulates, and sinks. The rain becomes part of the planetary core. Core processes may even feed the atmosphere. Volcanic outgassing is possible. Interior heat may add to the cycle. The atmosphere is not static, but fed. Fed by both star and planet, the weather endures. It is not a brief storm, but permanent climate. This permanence makes it all the more astounding. It shows stability in extreme forms. Forms of weather vary across exoplanets. Some rain glass, some snowstone. Some circulate water, some circulate iron. Each is a variation of one grand theme. Theme of universality is clear. Physics is constant. Condensation, wind, and circulation all apply. Only the materials change. Water here, iron there. WASP-76b is a new chapter in that story. Story continues with future telescopes. JWST will probe its atmosphere. More molecules will be detected, more clouds mapped. The rain of iron will be studied in detail. Detail will reveal whether rain reaches depth. Perhaps it evaporates again before falling. Perhaps only droplets reach lower layers. Perhaps storms are more chaotic than we know. Know for now that iron rain is real. Know that the atmosphere is violent. Know that this planet is an icon of extremes. It is one more reminder that reality is wider than thought. TRES-2b is our next stop, a world that orbits its star in the constellation Draco about 750 light-years away, first discovered in 2006 by the Transatlantic Exoplanet Survey. Close to its host star, with a year lasting just 2.5 Earth days, it remains tidally locked so that one hemisphere faces unending daylight while the other rests in eternal night. The host star is a yellow dwarf, not very different from our Sun, and yet what orbits it is something we had never imagined. This world is known as the darkest planet ever observed. The measured reflectivity, or albedo, is less than 1%. Light from the star falls onto its atmosphere, but almost none returns. It absorbs nearly everything, glowing only with the faint red of its own heat. The planet appears darker than coal, asphalt, or even the blackest paint. Paint, like Vantablack on Earth, absorbs 99% of visible light. TRES-2b matches that feat on a planetary scale. Imagine a sphere larger than Jupiter, yet almost invisible against the void of space. It is a cosmic paradox, massive and bright in heat, yet visually black. Most gas giants are reflective. Jupiter reflects nearly half the light it receives thanks to ammonia clouds. Neptune reflects even more, its atmosphere scattering sunlight into blue. But TRAS-2b hides everything, a planetary shadow. Shadow, here, does not mean absence of matter. The planet is fully there, a giant envelope of hydrogen and helium. But its atmosphere is laced with absorbing chemistry. Molecules and atoms swallow photons instead of scattering them. Scattering is what gives Earth its blue skies. It is what makes Venus shine bright in our night sky. It is what paints Saturn's rings and Neptune's haze blue. Without scattering, darkness becomes the default color. Color on TRAS-2b is deceptive. In visible light, it is black, but in infrared, it glows faintly red. The heat signature shows temperatures above 1000 Celsius. It is a smoldering coal wrapped in endless night. Night and day mean little here because the planet is locked. One side is forever illuminated, the other in permanent darkness. But neither side reflects light in ways our eyes would see. The whole sphere is a body of endless absorption. Absorption may come from sodium and potassium vapors. These elements absorb strongly in the visible spectrum. Titanium oxide and vanadium oxide are also possible agents. Together they make the sky into a light-eating furnace. Furnace chemistry is consistent with high heat. At 1000 degrees, molecules are excited. Electrons absorb photons easily, producing blackness. The atmosphere is not reflective, but purely hungry. Hungry for light, the planet swallows all wavelengths. It does not even shine like Jupiter with bands. There are no reflective zones, only blank dark. It is the closest thing to a cosmic hole. Hole is not literal, of course. Unlike a black hole, this planet does not trap light gravitationally. Instead, it captures light with atmospheric chemistry. It is still matter, still a giant globe. Globe of gas but inflated. Its radius is larger than Jupiter, yet its mass is only slightly greater. That makes it less dense, a puffed-up giant. This puffiness makes its absorbing layers thicker. Thicker atmospheres mean more photons are captured. The path length through haze is long. Light cannot escape once absorbed. It is converted quickly into heat. Heat defines its appearance. Spitzer recorded its infrared emission. The day side glows faintly like a hot ember, but the glow is weak, not enough to brighten its face. Face of TRAS-2b is therefore invisible to ordinary sight. Kepler monitored its phase curve. It revealed brightness variations at levels of less than 1 part in 10,000. This is the faintest planetary reflection ever measured. Measured brightness was so low astronomers doubted at first. They asked if the signal was noise. Repeated analysis confirmed the truth. The planet is indeed almost perfectly black. Black in this sense means featureless, no bright zones, no reflective bands. The only visible effect is the star's shadow during transit. It is a silhouette, nothing more than a bruise on starlight. Starlight reveals mass and radius. Transit depth shows size, radial velocity shows weight. Together they confirm a gas giant of Jupiter's class. But the optical brightness is far below expectation. Expectation was that hot Jupiters would shine. Their clouds should reflect light. Their albedos should be at least a few percent. TRAS-2b violated that rule. Rule breaking forced new theories. Maybe clouds are absent, burned away by heat. Maybe metallic oxides dominate, absorbing all photons. Maybe pressure broadens absorption lines into deep bands. Bands of absorption spread across the spectrum. They leave little chance for light to escape. The result is a spectrum as flat as soot. The planet is covered in atmospheric tar. Tar is a crude comparison, but effective. On Earth, tar roads reflect little light. They appear black under bright sun. Tries 2b is the tar of the cosmos, stretched into spherical form. Spherical blackness is unsettling. From afar, the planet would look like a void. Not a star, not a reflection, just emptiness where a planet should be. It is a shadow cast into orbit. Orbit itself is stable but close. Every 2.5 days, the planet completes its path. Tidal forces keep it locked, day and night forever fixed. The star dominates its entire planetary existence. Existence of a world this dark raises questions. If atmospheres can be so absorptive, what else is possible? Could there be planets of pure metallic clouds? Could there be atmospheres darker than even this example? Example worlds exist. WASP-12b reflects slightly more. HAT P7b reflects through sapphire clouds, but none match TRES-2b in perfect darkness. Darkness here is not absence of heat. The planet glows, but only in infrared. To the eye, it is gone. To instruments, it is blazing. This dissonance makes it a planetary ghost. Ghost is a fitting metaphor. It drifts across its star as a shadow. It reveals itself only in fleeting glimmers. Otherwise, it is invisible in reflected light. Light is what defines most planets for us. We see Jupiter as striped, Neptune as blue. We see Venus as brilliant, Mars as red. TRES-2b denies us that sight. Sight cannot reveal its character. Only instruments can, through curves and spectra. It is the science of absence, detecting what is not there. It is a study in the art of missing. Missing brightness changes how we think. A planet does not need to be bright to exist. It does not need to show us reflective seas. It can be defined by what it absorbs. Absorbs is the right word. It eats light like a bottomless well. It leaves almost nothing to shine. It is a masterclass in planetary consumption. Consumption of photons changes climate. Energy becomes heat. Heat drives winds, circulation, storms. But none of this is visible to human eyes. Eyes expect contrast, glint, sparkle. Here there is none, only matte. The whole world is a soft black sphere. It is invisible, yet undeniable in its gravity. Gravity ensures the planet endures. Despite losing heat, it does not evaporate. Its mass is large, its pull is strong. It resists even while it burns. Burns faintly, radiating red at night. The ember glow is weak. Kepler caught it only with unmatched precision. This made TRES-2b the darkest confirmed planet. Planet, but also a symbol. A reminder that expectation can be wrong. A reminder that categories need constant revision. A reminder that discovery means facing the unexpected. HAT P7b is the next world in our list, a gas giant that orbits about 1,000 light-years away in the constellation Cygnus, first detected in 2008 through the transit method. Close to its host star, with an orbit of just over 2 Earth days, it endures irradiation fierce enough to melt most metals. The host is an F-type star, larger and hotter than the Sun, a furnace that never allows its innermost companion a moment of reprieve. This planet is one of the most chaotic weather worlds yet measured, a place where clouds are born from minerals, and storms rearrange the skies on a scale that defies our sense of climate. The planet is slightly larger than Jupiter, but about 1.8 times as massive. Its density is moderate. but its atmosphere swells under heat into a restless envelope. What makes it remarkable is not just the heat, but the variability of its brightness. Unlike many hot Jupiters that remain stable, HAT P7b flickers. Flickers in light curves are not noise, they are weather. Kepler, which stared at this world for years, recorded shifting patterns. Brightness rose and fell unpredictably, as though clouds were appearing and vanishing. The explanation is violent winds reshaping the atmosphere day by day. Winds here are unlike any on Earth. They race at thousands of kilometers per hour. They transport heat from the eternal day side toward the night. They also push clouds of exotic minerals across the globe. Minerals matter here because the atmosphere is so hot that water clouds cannot form. Instead, clouds are made from corundum, the mineral that produces sapphires and rubies. Imagine skies streaked with crystal dust, reflecting light in shimmering colors. This is not fantasy, but mineral physics. Physics dictates which molecules can condense. At 2500 Kelvin, only the most refractory species survive as particles. Corundum is stable, and so crystals of aluminum oxide float. These crystals build the first alien clouds made of gemstones. Gemstone clouds are transient, carried by winds and then destroyed. The circulation moves heat unevenly, so condensation zones shift. Clouds may form, then dissipate as temperatures change. This cycle creates the observed variability in brightness. Brightness is measured during transits and eclipses. Kepler recorded subtle shifts in phase curves. Some nights the night side glowed brighter. Other nights it was dim. The conclusion is active weather, dynamic and violent. Violent storms dominate the night side. As winds carry heat, convection drives rising currents. Clouds appear in patches, then vanish. The planet is not steady but unstable. Unstable planets tell us atmospheres are not simple blankets. They are restless machines powered by starlight. On HAT P7b, the machine is in constant flux. No two orbits are ever exactly the same. Same cannot apply here. Every orbit, the planet changes. Clouds reassemble, winds redirect. The climate is forever being rewritten in mineral dust. Dust of sapphire and ruby storms has a poetic ring, but for astronomers it is a measurable effect. The albedo varies, colors shift. This is gemstone rain on a planetary scale. Scale is immense, far beyond earthly hurricanes. A single storm can span the entire hemisphere. Winds roar faster than any terrestrial jet. Lightning may flash in clouds of mineral crystals. Crystals at high altitudes scatter starlight. This scattering makes the planet brighter on some nights, but as the winds shift, clouds are torn apart. Then the planet grows dark again, heat escaping freely. Freely escaping heat makes the planet glow in infrared. Spitzer recorded dayside temperatures above 2600 Kelvin. The night side remained hot, above 1500 Kelvin. The redistribution is incomplete, but still intense. Intense contrasts mark the Terminator line. Day is an oven of gas, night is slightly cooler. Between them lies the boundary of rushing winds. Here, the most violent storms may form. Models show giant jets carrying material eastward. The hotspot is displaced, shifted from the substellar point. This proves winds dominate the circulation pattern. Other hot Jupiters remain steady. This one flickers with orbital cycles. Its weather is not predictable, but chaotic. Chaotic does not mean random. It follows physics, but the feedbacks are sensitive. A slight shift in temperature changes cloud formation. A small change in winds alters global brightness. Brightness fluctuations were the first exoplanet weather detected. Kepler's data revealed true atmospheric dynamics. This was not static absorption, but mobile clouds. It was proof that alien skies are alive. Alive in the sense of motion, not biology. Clouds form, dissipate, and return like living breaths. The atmosphere exhales crystals, inhales heat. This rhythm makes the planet visibly change. Change is the theme of HAT P7b. It is never the same world twice. Every orbit rewrites its atmospheric map. Every storm redraws its face. Face in optical light shows gem clouds. In infrared, it shows hot winds. In spectra, it shows sodium and titanium oxide. Together, they build the portrait of a stormy giant. Stormy giants like this refine models. They show that clouds need not be water. They show that storms need not be gentle rains. They show that weather is a universal but varied phenomenon. Varied mineral weather pushes our imagination. Rain of rubies, hail of sapphires, winds of dust. What is exotic to us is ordinary there. It is only the local rules of chemistry. Chemistry is not exotic, it is just shifted. On Earth, aluminum oxide is solid. On this planet, it is a drifting cloud. The difference is only temperature. Temperature is the true sculptor. It decides what condenses, what evaporates. It creates gemstone clouds here, iron rain elsewhere. Every hot Jupiter is a laboratory of heat. Heat keeps the planet inflated. Its radius is larger than expected for its mass. This means some internal heating occurs. Perhaps ohmic dissipation, perhaps tidal flexing. Flexing from tides may add to storms. The orbit is close, gravity is strong. The interior may be stirred, adding energy. This makes storms even more vigorous. Vigorous winds keep the climate in balance. They prevent one side from burning to ash. They spread heat, they form clouds. They sustain the cycle of sapphire storms. Storms make the planet beautiful in a strange way. They are violent but also glittering. Imagine skies streaked with corundum dust. Every sunset is a storm of ruby shards. Shards are not metaphors alone. Particles of aluminum oxide may truly fall. They would sparkle if viewed up close under light. They would cut across horizons in endless showers. Showers of gems sound unreal, but the data is solid. Spectroscopy reveals aluminum and titanium oxides. Variability proves clouds must form. Physics requires mineral condensation at those heights. Heights in atmosphere are where temperatures allow survival. Deep layers are too hot, crystals melt. High layers are cool enough for dust. So corundum drifts like thin cirrus clouds. Clouds change planetary brightness. They reflect more light. When they vanish, absorption dominates and darkness returns. This explains the flickering orbital signal. Signal analysis is now routine. Kepler gave the first hints. TESS and Hubble confirm. Each telescope sharpens the picture. We can almost watch weather across alien skies. Skies that are forever storming. Unlike Earth, where calm is normal, this planet knows no pause. It is an atmosphere in permanent motion. It is a giant caught in eternal instability. HD 106906b is our final stop, a planet discovered in 2013 with the Magellan telescopes in Chile, orbiting a binary star system in the constellation Crux about 336 light-years away. Close is not a word that fits this world because its distance is extraordinary. More than 730 astronomical units from its stars, over 20 times farther than Pluto is from the Sun. The host stars are young twins, only about 15 million years old, blazing brightly and wrapped in a wide debris disk of dust. And far outside that disk, drifting almost alone, lies a planet with no right to exist. The planet is massive, about 11 times the mass of Jupiter. That makes it nearly at the edge of becoming a brown dwarf. Its radius is still planetary, but its gravity is fierce and its brightness high. This is a world glowing faintly with the residual heat of formation. Heat at such a distance is not from starlight, it is intrinsic, left over from collapse. At hundreds of AU, stellar radiation is too weak, so the glow is its own fading memory. Memory of formation is where the paradox begins. Planets form in disks of gas and dust around stars, but that disk thins and vanishes long before such distances. No core could accrete gas at 730 AU, not in any known model. Models of planet formation suggest two routes: core accretion, where dust clumps into rock, then gas, or disk instability, where gravity collapses gas directly. Neither works so far from the central light. Light from the stars is weak at this orbit. The protoplanetary disk would have been too thin. No matter how much time we give, accretion fails. Disk instability also fails because density is too low. Failing models mean this planet must have formed elsewhere. Perhaps it was born closer and scattered. Perhaps sibling stars tugged it outward with gravity. Perhaps it is a captured object stolen from a neighbor. Neighbor systems can exchange bodies during chaos, but the orbit of HD 106906b is still bound. It circles the twin stars on a wide path. That binding itself is a quiet miracle. Miracle not in a mystical sense, but in probability. At such a wide distance, the slightest nudge could eject it. A passing star could free it into interstellar space, yet it remains attached, circling like a patient ghost. Ghost planets like this blur the line with stars. At 11 Jupiter masses, it sits just below fusion. Had it been larger, it would glow by deuterium. It is a near miss, a failed star. Star or planet, the categories grow thin. This world exists in a liminal zone, too far out to be ordinary, too small to be a sun. It is a reminder that nature ignores neat labels. Labels we invent, but the cosmos does not care. For us, a planet must form in a disk. For nature, it simply exists, whether or not it matches our textbook. HD 106906b is the ultimate planetary rebel. Rebel worlds like this teach humility. They force us to accept the limits of our theories. They prove that discovery is not about comfort, but confrontation. We are confronted here with a body that should not be possible. Possible alternatives include capture from interstellar space. Perhaps it was a rogue planet wandering alone. The young binary might have snared it with gravity. If so, it is a refugee folded into new family. Family is a loose word for a system so unstable. The debris disk around the stars is tilted. The planet's orbit may be misaligned, pulling at the disk. This system is a dance of imbalance and strain. Strain shows in the disk's warped shape. Astronomers suspect the distant planet sculpts it. Its gravity may shepherd dust, carving gaps. The system is evidence of dynamic conflict. HD 106906 is young, still wrapped in dusty veils. Planets migrate, orbits shift, resonances break. This giant may be the survivor of violent scattering. Scattering is when gravitational encounters hurl planets outward. One world dives inward, another is flung. This one may be the flung survivor. It rests now at the system's outer edge. Edge, in this case, means exile. It circles far beyond the warm zone. It receives little light, little warmth. It is frozen, yet still glowing with its own heat. Heat here is not gentle, it is internal contraction. Young giants radiate energy as they cool. At 15 million years old, this planet is still bright. We see it directly, imaged as a glowing point. Point sources of light beyond stars are rare. Most exoplanets are inferred, not seen, but this one is directly imaged. Its distance makes the star's glare less blinding. Blinding light usually hides close-in planets. Here the planet is remote, far enough for separation. Telescopes captured it as a dim companion. The sight is a triumph of observational patience. Patience is key because wide orbits take millennia. We cannot watch it move in a human lifetime. Its orbital period may be tens of thousands of years. We see only a snapshot of cosmic motion. Motion at that scale feels eternal. The planet is frozen in its vast arc. Its stars are tiny points even from its surface. It circles in a night sky of endless darkness. Darkness defines its solitude. It does not bask in the warmth of light. It does not glimmer with reflected glow. It lives in the margins of its system. System boundaries may blur with interstellar space. At 730 AU, the Sun's Oort cloud would already begin. This planet drifts at the edge of capture and loss. It is nearly a rogue, nearly gone. Gone worlds like this may be common. Rogue planets outnumber stars in the galaxy. Most are undetectable, drifting in silence. HD 16906b is a rare caught survivor. Survivor status gives us a window. We can study its atmosphere, its composition. Spectra show methane and clouds of silicate dust. It resembles a young brown dwarf. Dwarf status is a razor's edge. At 11 Jupiter masses, it is borderline. It could be planet or failed star. Its label depends on birth history. History is uncertain. Did it form in a disk and get scattered? Did it collapse directly like a star? Did it wander in and get captured? Captured bodies are rare, but not impossible. Young clusters are crowded with stars and gas. Encounters are frequent, gravity plays. A stray planet can be folded into a new orbit. Orbit, so far out, is fragile. Galactic tides could strip it away. Passing stars could pull it free. Its grip on the system is tenuous, but lasting. Lasting for millions of years at least. For now it is stable, an outer guardian. It may shape the debris disk like a shepherd. It may echo the influence of distant Neptune. Neptune in our system shapes Kuiper belt edges. This planet shapes its disk on a vast scale. It proves that even distant giants leave marks. Gravity reaches far, even across cosmic margins. Margins are where the unexpected thrives. We once thought planets must be close. We thought disks ended at neat boundaries. This world proves the cosmos draws no lines. Lines of theory must bend. We adapt to new data. Every impossible planet is a new rule. Every paradox is a new lesson. Lesson of HD 126906b is that exile is possible. Planets can live far beyond their cradles. They can glow alone in cold orbits. They can survive outside the warmth of systems. Systems like this remind us of scale. Our solar system feels vast at 30 AU. This world lives at 730, a wilderness of distance. The sheer gap humbles our perspective. Truth is that the cosmos is stranger than we dreamed. It holds lava oceans, sapphire clouds, iron rain. It holds burning ice, diamond mantles, and coal dark skies. It holds giants adrift at the edge of their suns. Suns, burn steadily, but planets wander. They migrate, inflate, evaporate, or persist. They show us survival in every form. They prove that nature's imagination is greater than our own. Own theories will change, rewritten by discovery, but the planets remain, circling in patient silence. They do not care for rules or human limits. They exist simply because they can. Can is the only law the universe obeys. If physics allows it, the cosmos will make it. If chemistry permits, the cosmos will shape it. If gravity holds, the cosmos will keep it. Keep this thought as we close. We began with swollen giants and burning oceans. We wandered through diamond worlds, dark spheres, and iron storms. We end with a planet exiled but still bound to its stars, but only barely. It circles at the edge of freedom. It is both planet and failed star. It is both exile and member of a cosmos that knows no order but possibility. Each impossible planet has shown us a new face. Each paradox has revealed a deeper truth. That truth is simple: the universe is strange. Strange and beautiful, relentless and precise. Planets with no right to exist are proof. Proof that we must let go of rigid expectations. Proof that reality is always wider than our dreams. Dreams end here, but the cosmos continues. Worlds beyond counting circle their suns in silence. Some burn, some freeze, some glitter, some hide. All exist because the universe allows the impossible.